Alright, so hello and welcome everyone to week 13 and the revision session for the uh, course on computational fluid dynamics for incompressible flows. As we all know, this course was being offered by NPTEL, being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm the TA for this course, and like every other week, we shall be solving some problems together. Let's dive in. So we have question number 1, asking us to arrange the main steps involved in solving a CFD problem in the correct sequence. So, the steps being from A to D. Step A, solving the discretized equations until convergence. Step B, geometry and mesh generation. Step C, problem setup, selecting appropriate equations, boundary conditions, discretization schemes, etc. And D, post-processing, involving visualization and data analysis. So once you arrange them in a correct sequence, there could be 4 options as the options given below. So option A being CBAD, option B being BACD, option C being BCAD, and option D ABCD. So go through the steps carefully, arrange them in a correct order, and then see if you can find your correct order in the options given below. Let's take a look at the solution. It's actually option C, BCAD. So first step obviously is to generate the geometry and mesh. So let's say if you're trying to solve for flow through parallel plates, then this geometry you have to create, you have to specify the lengths and dimensions, all the dimensions you have to specify. Then you need to divide this up into smaller discrete control volumes as well, which is mesh generation. So that is step 1. Then step 2 would be to set up the problem. You have to select the appropriate equations, meaning what do you want to solve for? Do you want to solve for fluid flow? Is it laminar? Is it turbulent? What kind of a model do you consider? Similarly, you need to specify the boundary conditions. So let's say inflow boundary conditions in the inlets, then outflow boundary condition in the outlet, and the wall boundary condition, whether you want to use a slip wall or a no slip wall, you have to fix those things. So that becomes your second step. And the third step is to, once you have all this, you solve the discretized equations using whatever scheme you decide until convergence, and that gives you the solution. Now the solution is in the form of numbers, just matrices of numbers. That's not really helpful or easy to understand, which is why you need the last step, that is post processing, where you visualize that data in a more, what can I say, in a more visually appealing way. It may be in the form of graphs, it may be in the form of contours, plots, and so on. And you can analyze some data as well depending on the needs of the problem. So the correct sequence which is followed in solving a CFD problem is uh, B first, then C, then A, and D at last. So BCAD option C should have been the correct answer. Alright, so we'll move on. We'll move on to question number 2, which is asking us to classify the following partial differential equation into whether it's hyperbolic, elliptic, parabolic, or any of the above. So the equation is this. It's dou 2u, dou eta, dou zeta equal to 0, and here are the options. Option A hyperbolic, option B elliptic, option C parabolic, or option D any of the above. So try to classify this equation and then select your option, select your answer from the options given below. So let's take a look at the solution. It's option A, hyperbolic. Let's see how we do that. So this equation is nothing different than simply, in a more familiar way, it's like dou 2 phi dou x dou y being equal to 0. And if we compare with the uh, general form of a partial second order partial differential equation, then it looks something like this. So a dou 2 phi dou x square plus b dou 2 phi dou x dou y plus c dou 2 phi dou y square, then d dou 2 phi dou x into E dou phi dou y plus EF, then F phi plus some G equals 0. This is the general form. Now, comparing with the general form, we have the values of A equals 0, B equals 1, C equals 0. These are only the three things that we need to determine whether it's hyperbolic or not. We find out what the value of b squared minus 4ac is. So it's simply 1 squared minus 4 into 0 into 0 being 1, which is obviously greater than 0, meaning it is hyperbolic. So option A should have been the correct answer. Now, if instead it was less than 0, then it should have been elliptic, and if exactly equal to 0, then it should be parabolic. This is how we classify partial differential equations, and their behaviors as well as solution methods depend on that. Alright, so moving on, we'll move on to question number 3, asking us what is the order of accuracy for forward difference approximation of a second order derivative using 3 points. So there are three important pieces of information given. It's that you have to find a second order derivative, which is something like dou 2 phi dou x2 using a forward difference approximation using 3 points. And you have to find out what the order of accuracy is. Is it option A 2, option B 1, option C 0, or option D insufficient data? Let's take a look at the solution. It's actually option A 2. So since you have to use 3 points and in the forward difference approximation, so it's like if you're trying to evaluate at point I, you need 2 more points, I plus 1 and I plus 2, and this is your dou 2 phi dou x2 over here. So for a double derivative, you need a minimum of 3 points. You can't really find a double derivative with just 2 points. So there are various ways of finding this, where you can, write this derivative in this form: alpha into phi I plus beta into phi I plus 1 plus gamma into phi plus 2. Then you expand these in the Taylor series expansions, and then you determine what alpha, beta, and gamma is. But while doing that, if you're using only 3 points, you have to leave out higher order terms of order delta x squared, meaning that the order of accuracy would be 2. Now, instead of 3 points, had you used 4, your order of accuracy would have been 1 extra. It would have been 3. So if you had used 5 points, it would be 4, and so on. Okay. So moving on, we'll move on to question number 4 now, which is a numerical type question asking us what is the maximum time step that can be used if you're trying to obtain a stable solution for Stokes' first problem using a FTCS method with so and so parameters. The momentum diffusivity or the viscosity is given, as well as the spatial derivative delta y is given as 3 millimeters. This, and so a quick refresher. Uh, Stokes' first problem is the problem of a suddenly started infinite plate. So imagine this, a plate was stationary and there was some fluid on top of it, and this plate is infinitely long, and you suddenly start moving the plate with a certain velocity u. So what happens as a result of that is that it sets up a velocity field in the uh, fluid above it due to viscosity. So this is sort of the velocity profile, and it evolves over time as well. So given this, what is the maximum time step that you can use? One other piece of information that the flow equations in this case boil down to a parabolic set of equations, which is like dou u dou t equal to nu into dou to u dou y squared. So you have to use a FTCS scheme which is conditionally stable, and the condition for stability in FTCS schemes or parabolic schemes is something like this, where your gamma x or gamma y that has to be less than equals half, and this gamma can be written as capital gamma, which is the diffusion coefficient into uh, time time discretization divided by spatial discretization, which has to be less than equal to half. And this capital gamma over here is nothing but nu, so we'll replace that. So nu into delta t over delta y squared has to be less than equal to half. Now if we rearrange these equations a little bit, so then it comes out that delta t has to be less than delta y squared divided by 2 into nu. So since it has to be less than equal to this, the maximum value would be exactly equal to this. So delta T max would be equal to this number over here. So we'll plug in the numbers. So delta y is 3 millimeters. So it's 3 into 10 power minus 3 meters squared divided by 2 into nu, which is 1.5 into 10 power minus 5, and this is given in SI units, meters per second. So 1.5 into 10 power minus 5 is typically the viscosity for air. So let's solve for these numbers. So 3 squared is 9, 10 power minus 3 squared is 10 power minus 6, 2 into 1.5 is 3, and we have 10 power minus 5. So 3 and 9 cancels out to give me 3, and these two cancel out to give me 10 power minus 1. So it's basically 0.3, or as the option says, 3 into 10 power minus 1 seconds. So this is in seconds. So it should be option A. Yes, indeed it is option A. So this is how you uh, test the stability condition for FTCS schemes, and you can get the maximum time step which you can use. So you have to use some time step which is at least that much, or at most that much, or less than that. Alright, so moving on to question number 5, which is asking us which scheme is employed by the CIR method. So just a quick refresher, CIR method is the Courant, Isaacson, Rees method, and which scheme is employed by it? Is it FTFS, FTBS, FTCS, or first order upwards? Let's take a look at the solution. Sorry, it's the first order upwind scheme. So CR method actually combines FTFS and FTBS into a neat little form where you don't need to worry about the direction of flow. So what CR method does is, let's say if you're trying to evaluate dou phi dou x at a certain point, at let's say point I, then you can simply write it as u, sorry, mod u plus u divided by 2 mod u. So this is when u is positive. So then your upwind scheme should have been Phi minus Pi minus 1 divided by delta x. So this is your template. You have I over here, I minus 1, I plus 1. So when u is positive, your upwind point is I minus 1. That's why you use this. And for the other scenario, when u is negative, or in the other direction, so then you take the difference between mod u and u and divide it by 2 mod u, and in this case your upwind point is I plus 1, so you write the derivative as I plus 1 minus I divided by delta x. So this sort of gives us a neat little way of writing the derivative of x involving so that we can implement first order upwind scheme no matter which direction u is blowing in. Okay. Alright, so moving on, question number 6. It's asking us which of these methods use both FTCS and BTCS methods. Is it option A, midpoint leapfrog method? Is it option B, CIR method? Is it option C, McCormack method? Or is it option D, both B and C? So FTCS and BTCS, meaning forward time central space as well as backward in time central space. Let's take a look at the solution. It's actually the McCormack method, which is a multi-step method. So in this, when you are going from, let's say, time level n to n plus 1, you, you usually use an intermediate time step as well, n plus half. So while going from n to n plus half, you might use the FTCS, and then going from n plus half to n plus 1, you use the BTCS. So you use a combination of implicit as well as explicit schemes, and this ultimately results in a solution which is unconditionally stable. And you can use the other way also, like you can use BTCS first and then FTCS as well. So that is what the McCormack method does. Alright, so moving on, we'll move on to question number 7. We have the same options for a different question this time. It's asking us which of these methods have order of accuracy 2 in both time and space. Is it option A, midpoint leapfrog method? Is it option B, CIR method? Is it option C, McCormack method? Or is it option D, both B and C? Okay, so let's take a look at the solution. It's actually option A, midpoint leapfrog method, which is nothing but a CTCS method. So use a central in time, central in space discretization. So if your original equation is something like dou phi dou t equals some, gamma dou 2 phi dou x squared, then you discretize it as, phi I n plus 1 minus phi I n minus 1. So at n you take a central difference divided by 2 delta t, and on the right hand side you take a spatial derivative at time level n. So you have phi I plus 1 minus 2 phi I plus phi I minus 1, and all of them at time level n. And it's divided by delta x squared. So this first derivative, this gives you order delta t squared accuracy, and spatial derivative also gives you order delta x squared accuracy. So your order of accuracy is 2 in both time as well as in space. So that's the midpoint leapfrog method. Alright, moving on. We'll move on to question number 8, which is asking us match the following in relation to numerical effects in modified equations. So, even terms, odd terms, these are the two options on the left hand column A, B, and on the right hand column we have wiggles and smearing 1 and 2. So you have to match the following. There are only two options. It's either A1 B2 or A2 B1. So which terms in the modified equations lead to what? So in the upwind schemes, the discretization method leads to some discretization errors, uh, introducing some extra terms which are in the modified equations, which result in some erroneous numerical effects. Now, which derivatives, even derivatives or odd derivatives, lead to? So let's take a look at the answer. It's A2B1. So what happens is even terms, they lead to something called dissipation, leading to smearing. So A2. Whereas odd terms, they result in something called dispersion, resulting in wiggles forming in the uh, solution. So let's say if your correct solution was this, dissipation would give you something like this. It smears away the sharpness, whereas the odd terms, they will result in some wiggles forming like this in the solution, and this is known as dispersion. So the correct answer would be A2B1. Alright, so we'll keep rolling. We'll move on to question number 9, which is asking us what is the main advantage of using the stream function vorticity formulation in computational fluid dynamics? Is it option A, reduces the number of equations or variables to be solved? Is it option B, increases accuracy? Is it option C, both A and B? Or is it option D, none of the above? Let's take a look at the solution. It's actually option C, both A and B. So what happens is, let's say in a 2D case where you have u, v, and p to be solved using three equations, you transform it to just psi and omega, which are governed by two equations. So from three variables, three equations, we go down to two equations, two variables, and that reduces the computational effort required to be put in, and it also increases the accuracy because let's say you find psi with some order of accuracy, you know, delta, uh, some order of accuracy n maybe. Now, since u is given by dou psi dou y, so if psi you know with order of accuracy n, the derivatives of psi you can determine with order of accuracy n plus 1. So whatever order of accuracy you got while converting back to u and v, that order of accuracy increases by a factor of 1. So these are both advantages of using the stream function for vorticity formulation. So that's why option C should be the correct answer, both A and B. Okay, moving on to the last question of today's session, which is asking us in the quick scheme, how many grid points are typically considered for interpolation? Is it option A 2, option B 3, option C 4, or is it option D 5? So, quick reminder of the quick scheme. The full form of it is quadratic upwind interpolation for convective kinematics. Or convective kinetics. So how many grid points are used? Let's take a look at the solution. It's actually 3. So what happens is, let's say if you are trying to find out the upwind version of P, so not P, so let's say this is my template P, E, and E, E. So usually you use a staggered grid, and this is the point where you have to find out some derivative, something like, let's say, dou 2 phi dou x2 or something like that. So for that, you use 1 point to the left and 2 points to the right. So total four, total 3 points are used for these interpolations. And so let's say for dou phi dou x, you use these 3 points and you get a quadratic order of accuracy. Alright, so that's all for today. Thank you.